Okay, we're on chapter 4, and last week we were talking about the atom here. Come here. We talked about the atom that's mostly empty space. Has again a positive nucleus, which has protons in there and also neutrons. We have electrons out in that empty space moving around the atom. Again, most of the mass of the atom is made up of the nucleus, which has both protons and neutrons, which are each quite much heavier than any electron that's flying around. Then we got into atomic number, which is the number of protons there are in an atom. Again, the atomic number can be found on the periodic table. It is that number above the symbol. And again, as we talked about, every single element has a different atomic number, which means out of protons, electrons, and neutrons, it is the protons that's the most important in terms of what element it is, as that will determine if you're dealing with, for example, hydrogen, lithium, or what it may be, magnesium. We also have the mass number, which is our number of protons plus our number of neutrons. And that, again, is not found on the periodic table. So, again, that is not the number that's underneath the symbol, as that is the atomic mass that we'll talk about. And, again, if you use both of those numbers sort of together, if you take the mass number minus the atomic number, that will give you your number of protons. So, again, that is the way you could count the protons, or not protons, neutrons. Let's try that again. Number of neutrons in that case. One way that we write sort of the symbol for isotopes, and isotopes again are the same element, but they have different masses because they have different numbers of neutrons. As we go with the symbol and we put the mass number up on top and the atomic number bottom left there. And again, if you take the top number minus the bottom number there, that will give you your number of neutrons. Pretty much all elements will have protons, electrons, and neutrons. The one exception is hydrogen. It has, again, just a proton and electron. It does not have a neutron. But again, that's a very common way we do that. We also talked about things with charges, which are ions. And again, if you have ions, there are cations, which are positively charged. There are anions, which are negatively charged. Cations are a result of losing electrons. And that's because at that point, if you've lost some electrons, you then have more protons than electrons. So you have more positive than negative. So you become positively charged. If you are an anion, you have gained electrons. And again, the opposite sort of definition there. If you've gained electrons, you now have more electrons than protons, so you're going to be more negative in that situation. How that affects, for example, something like this, if you did have a charge, as we talked about, since there's only really protons, which are positive charged, electrons, which are negative charged, and neutrons, which have no charge. Obviously, neutrons will have no effect on the charge. We can never change the protons, otherwise we change the element. So again, it is always the electrons that get changed in terms of when something gains a charge. And again, it'll have, thank you, more electrons if it's negatively charged, and the actual number is how many electrons it's gained from its neutral atom. So if it has a -2 charge, it means it has 2 more electrons than it normally would in its neutral state. And if it had like a +3 charge, it means it has 3 less electrons than it would in its normal state. Any questions on any of that stuff there? All right, so I think we are off to, I think we were talking about isotopes. And again, just to finish up on isotopes, again, one of the nice things about isotopes is because they are the same element, they will have very similar chemical sort of properties, if you will. And they will basically do the same sort of chemistry, all the isotopes. So for example, if you're interested in some type of element and what happens to it, say in a pathway or mechanism, you could use a radioactive version of that element, and you can follow exactly where it goes by following the radioactivity. So for example, if you had radioactive copper versus non-radioactive copper, they both will basically behave the same. It's just one has the ability, obviously, for you to follow the radioactivity. That's a very common process in research. They would sometimes use radioactive versions of elements just to follow where things end up along the way. Now let's talk a little bit about the periodic table. The periodic table there is obviously a table of elements there, and we have one on the wall there. It gives a great deal of information about the different elements. They were put together based on sort of common properties. They also, over the years, as they were sort of building the periodic table, left spaces to kind of fill in along the way. And one of the things we've seen, obviously, is something like the atomic number can be found on the periodic table. When we talk about the periodic table, uh, when we go up and down on the periodic table, that is what is referred to as groups on the periodic table. If you're super old and find an old book, sometimes people will call them families, but most people call them groups. And there's different numberings on the periodic table. For example, if you look at the one on the wall, or if you even look at the one we got up here, there's a bunch of different numbers you sometimes will see. There's sometimes, again, the A numbering. Sometimes there's the B numbering that you'll see as well through this part here sometimes. And you can just see as well just the 1 through kind of 18 numbering as you go left to right. So groups, again, kind of going up and down on the periodic table. We use in this class, and pretty much all chemistry classes that you take, we use what is sometimes referred to as the representative numbering, or the A numbering, and that is group 1 is here. By the way, group 1 does start with lithium, even though hydrogen is hanging out there, is actually not part of group 1. We'll talk why it's hanging out there in a bit, but that is what we start with group 1 with lithium. Group 2 is right next door. We skip the middle part, group 3, group 4, group 5, group 6, group 7, and group 8. So we go that way in terms of groups. Again, we skip kind of the middle section there in terms of numbering. Most people will just call it group 1, group 2, group 3, group 4, group 5, group 6, group 7. Most will not say like 1A, 1B, after 1A, 2A, 3A, although it is assumed that that is what you're talking about. Periods, on the other hand, periods go left to right on the periodic table. So we're going this way. There are 7 periods, 1, 2, 3, 4, 5, 6, 7 periods on the periodic table. And again, they go left to right. We also have seen there the number above the symbol is our atomic number, which tells us, again, our number of protons that we have in an atom. Now, when we look at the periodic table, it is broken up into sort of 3 categories of elements. We have metals, nonmetals, and semi-metals, or sometimes referred to as metalloids. A metal is a good conductor of heat and electricity. It is also can be hammered into sheets. It's ductile. It usually has a very shiny sort of appearance. Metals are typically solids at room temperature. The one exception is mercury. If you look at the periodic table on the wall there, Hg is mercury. It's actually blue, written blue. So a lot of times on periodic tables, we'll see it kind of written in a different color. And again, it's the only one that's a liquid under room normal conditions, as opposed to everybody else are solids. Typically, if you look at the periodic table, there's typically what is sometimes referred to as a staircase, starting around boron up here. And this staircase kind of coming down is almost a dividing line or transition point between metals and nonmetals. So kind of everything to the left is metals. Also the ones on the bottom, the 2 rows, those are also metals as well. Now, up to the right of the period of that staircase are nonmetals. So when we go up to the right here, we have our nonmetals. And our nonmetals pretty much have the opposite characteristics of metals. They're usually bad conductors of heat and electricity. They also are usually dull, brittle. They will also have a varied sort of state. So some of them are gases, some of them are liquids, some of them are solids along the way. So a lot of our nonmetals are those diatomic molecules that we talked about that are elements. So things like hydrogen, right? Nitrogen, oxygen, fluorine, chlorine, fluorine, bromine, and iodide. So these are all nonmetals. These, again, are those elements that come as diatomic molecules as well. Now, earlier we talked about group 1 over here, and it actually starts with lithium and not hydrogen, and that is because when we look at hydrogen, is what type of element? It is actually a non-metal. Yeah, so hydrogen is actually a non-metal, even though it's hanging out with all these metals over here on the left-hand side. So that is again why hydrogen is not part of group one, and group one starts with lithium, which is a metal. The reason hydrogen is hanging out over there is it has a lot of properties that are very similar to what we see with group one metals. And sometimes we actually kind of, in a lot of cases, treat it almost like a metal because we deal with hydrogen a lot in acids and in aqueous solutions. It has a +1 charge and behaves very similar to those in group one. But it actually is a non-metal. On older periodic tables, they used to put hydrogen on both sides, not too much anymore, but it actually is mostly over here these days. So that's something to keep in mind. Yeah. Hydrogen is not typically usually considered in any group. It's kind of just one. So sort of by itself, if you will. It's not really part of any group. Yeah. Other questions? All right, so the staircase there that comes down around boron, and some books will include boron. Those are metalloids or semi-metals, and the properties of metalloids are ones that fall kind of on either side of where they're located on the periodic table. So if you take a metalloid like one of these guys here, they will have several properties that people would say that's very much like a non-metal type property. And the same guy will also have some properties that are sometimes considered more metal type properties. And that does make sense if you think about sort of where they're located. As you go from a metal, you're transitioning kind of into non-metal territory here. So these guys here on the staircase have properties that kind of can fall on either side. And that's sort of why we have that sort of placement coming down. Now, some groups do have special names that you need to know about, and starting with group one here, those are our alkali metals. And once again, as we've been talking about there, starting with lithium, not hydrogen. Group two right next door, those are the alkaline earth metals. And alkaline pretty much means basic. So if somebody says make it alkaline, usually that means basic. And in group one and group two, that is where a lot of strong bases come from these groups. Things like sodium hydroxide, potassium hydroxide. Frankly, if you kind of go this way, and this way, and put OH with those guys, that is where, again, a lot of strong bases are generated from. Over here in group 7 are the halogens, and those are guys that mostly comes as twos, are fluorine, chlorine, bromine, iodide. And right next door is group 8, which is our noble gases. And as we'll talk about, noble gases are pretty much chemically inert. So group 1, alkali metals. Group 2, alkaline earth metals. Halogens, group 7. And noble gases, group 8. And some of those things, as we talked about there, halogens, again, they normally come as diatomic molecules. A lot of them are gases, like fluorine is a yellow gas, chlorine's a green gas, bromine's kind of like a vapor with a little bit of liquid with a little bit of vapor over it, and I2 is sort of a purple solid. They're very reactive. When we talk about reactivity of like nonmetals, right there around fluorine is the most reactive nonmetal you could have on the periodic table. And so a lot of those guys are very reactive as we go through it. Now, noble gases, as I mentioned before, are sometimes called rare gases, but most people call them noble gases. And when we talk about the two rows on the bottom, those are what are sometimes referred to as the lanthanides and actinide series. And that is because that's technically the two places where they follow. So if you follow the numbers here, we go from 57 to 72. The missing spot there is that top row. Here we go from like 89 to 104. Again, the missing spot there is that row, and they technically should be in there. They usually don't put it in there because your periodic table is pretty big if you do so. The only place I've ever seen it actually is like next door in that classroom there. It takes up the whole wall, kind of, because they had to spread the periodic table really out. So they've done that next door. Between group number 2 and group number 3, we have in this region here are transition metals. And transition metals are obviously metals, so they have metal characteristics. And one of the things that we'll learn about transition metals when we talk about naming, for example, is a lot of them have the ability to make a variable positive charge. So, for example, things like not carbon, things like copper can make +1 or +2 type charges. So, unlike sort of metals to the left there and group 1 and group 2, which has more of a fixed charge, as we'll talk about, these guys here in the transition metal region oftentimes can make multiple types of positive charges depending on the situation. That's also why these 2 rows on the bottom are sometimes referred to as inner transition metals, because they technically should kind of go in that middle spot there with the transition metals, but most people call them the lanthanide and actinide series. Now, obviously, the characteristic shape of the periodic table was placed with elements that has similar characteristics. So typically speaking, things in the same group, things kind of in the same period or near each other on the periodic table have very similar type properties. For example, the grouping of all these nonmetals together, they have similar types of properties, which affects how they, for example, interact with each other when they want to make something like bonds. And again, metals have very similar sort of interactions as well. And that's also why we get a pretty dramatic difference in an interaction when we take something from like the left-hand side of the periodic table and put it on with somebody on the right-hand side of the periodic table. We actually get things like electrons being transferred from one to the other because of those differences. So as we see, as we go from left to right on the periodic table, we're going from metals and then transitioning upwards into non-metals as we go across. Any questions on periodic tables there? So once again, you do need to know which way groups go, the numbering of the groups 1 through 8. You need to know periods. You need to know where atomic numbers found, and obviously metals, nonmetals, metalloids, which things are those, and some properties of them, and obviously the names of those groups: the alkali metals, alkaline earth metals, halogens, and noble gases. Any questions on that there? All right, so obviously a little bit more about noble gases. What noble gases are things that are chemically inert, which means that they really are unreactive. They typically do not react with others. They will react with themselves, but pretty much will not react with other things. There's also some noble metals. So things like gold, silver, and platinum are noble metals. So kind of in this area here on a periodic table. They also are very, very unreactive. You could put like a really strong acid, for example, on gold, and nothing much is going to happen to it if it really is gold. It will be pretty much unreacted. One of the things that we'll talk about when we talk about bonding is this group here, the noble gases, are really important. Really, the whole idea behind any type of bonding, be it ionic bonding, covalent bonding, where they share electrons, the goal pretty much of everybody, as we'll talk about, is to basically hit the same electron configuration as the noble gases, because the noble gases are really, really stable through bonding and making bonds. And even gaining and losing electrons, it allows certain elements to basically end up in a similar electron configuration as noble gases, and it creates a very stable situation and a stable bonding. So group 8 is really, really important, especially when we get into bonding. It is pretty much the goal of everybody to get themselves to that sort of situation. There we go, maybe. There we go. So again, as I mentioned, chemically inert. They're unreacted. They're usually colorless. By the way, most of the noble gases are monoatomic, which means they come as ones, unlike like hydrogen gas, nitrogen, and oxygen, which comes as twos. And then, like I said before, our silver, gold, and platinum are noble metals, very, very unreactive under normal conditions. And as we talked about there before, a lot of our nonmetals are our diatomic elements. So the structures of solid, we're just going to talk a little bit about solids for a second here. The structure of solids are a little bit more varied. Solids tend to form some different forms of the same elements. So if you have a solid that's sort of in a different form, that's sometimes referred to as an allotrope. And allotropes are basically the same element, but the way they're kind of put together and the arrangement of those atoms are different. So for example, carbon, there's a few different sort of arrangements of how carbon kind of comes together. One is like in a diamond, one is like graphite, like we find in pencils, and one's a fullerene. Fullerene is a giant arrangement of carbons, kind of pictured like a soccer ball sort of arrangement of carbons together. But this is all carbons, and again, in this arrangement, you basically get diamonds, which are a little bit more expensive than carbon in this arrangement, like pencil lead, and you get graphite here and more layers happening. So this sort of layering of the carbon atoms together gives us more of a lead type property. And obviously this non sort of layering of those carbon atoms gives us something like diamonds. And these are all referred to as allotropes. All right, so ions, which we touched upon as we were going through a little bit earlier on, just to remind everybody, an ion again is something that has a charge, and there are two types of ions. Again, a cation, which is positively charged, and we also have anions, which are negatively charged. But in a cation, it is a result of, as we talked about, somebody losing electrons. So when we look at sodium, it will lose one electron, and when it does, it will give off one electron here on the product side. And this is the way you could kind of write an equation or reaction showing the sodium losing an electron. And typically on the product side of the arrow, which is the right-hand side of the arrow, is typically where we put those electrons. Same thing here. If we look at magnesium, we could show the overall sort of situation that's happening. Magnesium will actually lose 2 electrons and become positively charged. And again, we will see those electrons on the product side to indicate that it is losing it. Remember, in a normal magnesium atom that's neutral, it has 12 protons and 12 electrons. In a situation here where it has a +2 charge, it still has 12 protons because it's still magnesium, but it has only 10 electrons. And again, that's where that +2 charge again comes from. Same thing with our sodium. In the neutral sodium, we have 11 protons and 11 electrons, which gives us an overall no charge happening. And when we look at the sodium with a +1 charge, it has 11 protons and only 10 electrons. And that gives us our +1 overall charge that we have here. So once again, it is the loss of electrons here. That is a cation. And once again, the actual charge tells you how many electrons it lost. This is a +2 charge, which means it lost 2 electrons from its neutral situation. This is a +1 charge, which means it's lost 1 electron from its neutral situation in this case. Now, aluminum has a +3 charge, which means it has lost 3 electrons. And neutral aluminum, it has, again, 13 protons and 13 electrons. Gives us, again, no charge overall. Aluminum with a +3 charge still will have 13 protons because it's aluminum, but only 10 electrons, giving us that +3 charge because it has 3 more protons than electrons in this case. By the way, in general, if you have an ion written, you should always have the charge written with it if it does have a charge. And the way that we name just simple ions, we actually just use the whole name. So this would be known as the sodium ion. If we had magnesium with a +2, this would be the magnesium ion. So if we have basic just cations, which are typically metals, if we had to name the ion, we basically just use the whole name of the element and just kind of put ion at the end. And also, again, if you were writing the formula like I did there on the left, if it is an ion that has a charge, you do need to include the actual charge with it. By the way, it is also important to remember, as we might have talked about previously, that if you take anybody off the periodic table by themselves, they do not have charges. Yeah, so things don't have charges if they are uncombined. Elements will only get charges when they start combining. More specifically, things will get charges when metals and nonmetals come together. That is typically where we get things that make charges. But if you again had for example, iron off the periodic table or a piece of magnesium off the periodic table just by itself, not combined with anything else, it does not have a charge. So sometimes people think they always have a kind of a charge. And if they're by themselves, they really don't. Any questions on that there? Now, anions, as I talked about, works the same way, except that they are negative charged. And again, we can represent that in an equation. Here, for example, chlorine plus an electron will give us chloride ion here. And here we actually see the electron on the reactant side. And that sort of indicates that the chlorine is going to actually pick up the electron. And if we want to be balanced about it, we know chlorine is one of those diatomic molecules that actually will come as a 2-pack there, which means you actually would have 2 electrons, 1 for each chlorine, and you would get actually 2 chloride ions on the right-hand side. Again, each one of them there is going to pick up an electron basically in this situation. Same thing here, if you had something like oxygen, it would pick up actually 4 electrons and would make 2O2 in this case. And again, that is because each individual oxygen atom is going to actually pick up 2 electrons and become negatively 2 charged. And again, here we see it on the reactant side to indicate that it's being gained. Now, when we see that negative charge has gained electrons, as neutral oxygen there is 8 protons and 8 electrons, gives you no charge overall. Oxygen with a -2 charge still will have 8 protons because it's oxygen, but it will have 10 electrons in this case. Again, 10 negative things and 8 positive things gives you that -2 charge that's left over. Same thing if we look at chlorine. Chlorine with no charge has 17 protons, which are positive. It also has 17 electrons, which are negative. And again, chlorine with a -1 charge, still going to have 17 protons because it's chlorine. We'll have 1 extra electron at 18 that gives us our -1 overall charge. Just like with the cations, when you see a charge that's negative, the negative tells you that thing has gained electrons from its neutral self, and the actual number of the charge tells you how many electrons it has gained. So if you have something like a -1 charge like we do with chlorine there, it has gained 1 more electron than it started with, basically. Yeah? And when we do name negative ions, we do something a little bit different in terms of naming the ion. So as you can see here, Cl minus. For negatively charged ions, we take the base of the nonmetal name and we drop the last part of the name and we actually put IDE at the end of it. So instead of chlorine, this becomes the chloride IDE ion. And O2 minus, instead of oxygen, we drop a little bit more than the last few, but that actually becomes the oxide ion. So anything with a negative charge that's a nonmetal that comes from the periodic table will get IDE at the end of its name. Just like with the cation, if you're going to write the formula for the Cl minus, that's an ion, you do need to include the charges to indicate that it is an ion. Any questions on that there? Now, there are certain things on the periodic table that can form sort of fixed charges, and they're really good to know as we get into some other things. Everybody in group 1 will form +1 charge. Everybody in group 2 will form a +2 charge when they do form it. Although on here there's multiple things listed. Typically in group 3, we're talking about aluminum, and that's usually a +3 charge. And skipping group 4 and coming down to group 5, typically those guys are -3 here. And we're talking about, by the way, the non-metals that are above the staircase, because we've got like the staircase kind of coming down through here. So the non-metals above the staircase in group 5 are -3, things like nitrogen, phosphorus. -2 for group 6. And again, the non-metals we're talking about here, and -1 there for our group 7. So it kind of goes +1, +2, +3 here on group 3. Skip group 4 and go backwards, -3, -2, -1. Now, most of the metals in the transition metal region have a variable type of positive charge. So for example, iron can be +2 in certain situations, and iron can be +3 in certain situations. And by the way, we sometimes will, because they can have different positive charges, we oftentimes will use a Roman numeral to indicate what the charge is. So iron 2 would have a Roman numeral of +2. I'm sorry, a Roman numeral 2 means that the charge has a +2 charge. Here the charge is +3, so we would actually call this the iron 3 ion. And the other guy, the iron 2 ion. Again, the Roman numeral indicates charge. We actually don't do that, for example, like the ones we did previously, like sodium. We don't have to worry about that because sodium has a fixed positive charge. You'll never ever find sodium in any other charge than +1. So because it's like fixed, it'll never change. You don't have to tell people, hey, it's going to be the +1 charge, because it always should be the +1 charge. So sometimes you'll see Roman numerals used, and we'll talk more about this when we get into naming officially. But sometimes you'll see Roman numerals used for transition metals to indicate the charge of that metal in that particular situation. Any questions on that there? Now, most metals in the transition metal region have a variable charge. There actually is 3 exceptions that don't have a variable charge, actually a fixed charge, and that is zinc down to cadmium, hang a left there to silver, this kind of backwards L right about here. These guys, even though they are transition metals, zinc and cadmium will always have a fixed +2 charge, and silver will have a +1 charge. So those are kind of 3 exceptions in the transition metal region, that even though they are transition metals, and even though transition metals typically have a variable positive charge, those guys are kind of locked into their positive charge. They will have a fixed positive charge. Any questions on that there? Now, compounds that contain ions, those are what are referred to as electrolytes. And electrolytes are substances that, when they go for a swim, they basically will break apart into ions. And the presence of these ions in a solution floating around basically will help, for example, it to conduct electricity. So the positive ions floating around the solution, or the negative ions floating around the solution, help sort of complete the circuit, if you will, and allow basically electricity to flow in that solution. And there are a few different types of electrolytes. There are strong electrolytes. And strong electrolytes will 100% break apart into ions. So for example, if you had a solution of sodium chloride, that was a solution, and this is the aqueous symbol, which typically is a water environment. It's basically a solution. In that solution of salt water, basically, you will have 100% sodium ions floating around and 100% chloride ions floating around. So you would have 100% of the ions floating around. You would have none of the sodium chloride units still together. So if you were to kind of toss that together and dissolve it in water, you would have just 100% of these positive ions floating around and chloride ions floating around. You would have none of them still together. Now, because of that, you have pretty much a ton of ions in that solution. It's going to conduct electricity really well. So it's going to be a very good conductor of electricity. So oftentimes with electrolytes, sometimes people use like a light bulb as an example. So if you had a light bulb that you connected to some wires and you put it into a strong electrolyte solution, your light bulb would turn on and be very, very bright. So it would just turn on like the light bulbs we got going on here. They'd be very, very bright. So you would have a very bright light bulb. Now, that is different than a weak electrolyte. A weak electrolyte will actually mainly stay together. But it will produce some ions. Yeah. So an example of that is hydrofluoric acid. Hydrofluoric acid is a weak acid. And when you have a solution of hydrofluoric acid, it will break apart into its ions, which is H plus and F minus. The difference, though, is here you will get a little of these guys formed. Bless you. But you will mainly have the whole HF together. So if you kind of looked at the beaker and you put some hydrofluoric acid in there, you're mainly going to have the HF guys still hanging out together. You will have a little bit of it that has broken apart into ions, but mainly it's going to kind of stay together. The result of that is it is going to produce ions, but not as much ions as a strong electrolyte. And because it still is able to create a little bit of these ions, you can still conduct electricity. So if you want to use sort of the light bulb example, if you took a light bulb that was connected to some electrodes and you put it into a weak electrolyte solution, the light bulb would turn on, but it would be super dim, like almost like it's dying. It would be very, very dim, not very bright at all, just barely kind of turning on. But it's still able to kind of turn on and conduct electricity because of that. Now, one of the major differences you typically will see in an equation, for example, of a weak electrolyte versus a strong electrolyte is actually the arrows. And in a strong electrolyte, it's like a one-way arrow, if you want. It's all going to dump out into the products. There's absolutely nobody going back the other way. In this way, this is what is known as a reversible reaction. And that means it actually goes in both directions. This reaction here on the bottom could go in the forward direction it's referred to, which is reactants going to products. But what happens is at some point you'll build up a bunch of these guys and they will start going the other way and it will go in the reverse direction. It's like a two-way street, if you will. It kind of goes backwards and forwards. It can kind of go in both directions. And that is, again, very different than a strong electrolyte, which is just a one-way. Everybody's going to break apart. Everybody's forming ions. And that's why the difference, for example, in the light bulb example, with a strong electrolyte, you get a very bright light coming on because there's a lot of ions in that solution, as opposed to a weak electrolyte where you got a little bit of ions, so still able to conduct electricity, but again, nowhere near the amount of a strong electrolyte. Strong acids, strong bases, ionic compounds like sodium chloride, those are typically strong electrolytes. They typically, when they're in solution, will not stay together. They're just going to completely break apart. A lot of weak acids and weak bases are weak electrolytes, and they mainly will stay together, like HF is again, a weak acid. Things like acetic acid is a weak acid as well. Our ammonia, NH3, is also a weak base. Now, the last type of electrolyte is really a non-electrolyte, and a non-electrolyte will dissolve but not create ions. So if you took something, for example, like sugar, and you dissolved it in some water, it's going to dissolve, right? It's a sugar. But since sugar is carbon, hydrogens, and oxygens, it will produce no ions. And because it produces no ions, no electricity is conducted. So there are certain things that could still dissolve, for example, but again, the lack of its ability to create any ions will prevent it from conducting electricity. Any questions on that there? So I guess I wrote over this picture. Let me get rid of that there. So again, this is the idea of the light bulb here in pure water. You can see the light bulb does not turn on. If you have pure water, that's H2O. That is held together by sharing of electrons. There's no ions present, and it should not conduct electricity, right? So water is actually a really bad conductor of electricity. Safety note, right, is the water that comes out of your pipes at your house is not pure water, right? And they actually put ions in your water a lot of times to clean it, and you will electrocute yourself, right? Because it's a very good conductor of electricity because of the ions and other stuff that's floating around there. But technically speaking, if you had just pure water, no ions in it, like deionized water, if you will, it will not conduct electricity because there should be no ions present in that. But in our house and stuff like that, obviously the water coming out does. If you throw a little salt, like some sodium chloride in here, as we talked about before, that's going to break apart into sodium ions and chloride ions. Now we have the positive, negative ions floating around that solution, and this light bulb is going to basically shine very brightly in that case, and that would be a strong electrolyte type solution. All right. Now, one last thing about sort of ions and putting ionic compounds together is whenever we have something that is a positive charge cation like sodium, which is group 1, and we want to put it together with a nonmetal anion, which is negative. Whenever we put these guys together, the overall charge has to equal 0. Yeah? So when you put them together, it has to equal 0. So in the case of sodium here, we have +1, which will balance out the -1, and this would be the formula for sodium chloride. Now, the formula here for this ionic compound is 0, but it actually is made up of things that have charges. So when you say you have a sodium chloride solution, you basically have two things that have charges. But when you write the formula for the ionic compound that comes together, when they come together, it should always equal 0. And it should equal 0, by the way, in the simplest way possible for it to equal 0. So for example, if we took group 2 calcium, which is +2, and we wanted to put it together with our group 7 chlorine, which is -1, once again, if I were just to put this together just the way it is, I would end up with CaCl plus. And that is because +2, right, and -1 equals +1 left over. So we definitely don't want to do that when we're writing the formula. So when we think about it, we want to balance it out. So we need not one chloride here, but we actually need two of them. -1 and -1 gives you a -2 charge that balances out the +2 charge here. So CaCl2. Remember that the number goes to the element to the left when you write the formula. So if there is nothing written like in the calcium, it means there's one of them. And if there's two, obviously written there for two chlorides. So this would be the proper formula that you would get when you put Ca and chloride together. This, by the way, is whole name of the metal, calcium, IDE for the nonmetal, chloride. Same thing here. This is sodium, whole name of the metal, IDE for the nonmetal, sodium chloride in this case. So whenever you again put those things together, you want to get it to equal 0. So let's take a look at a couple here. If I wanted to put Ba2 plus together with O2 minus, once again, we need to equal 0. And very much easy here. We just need one of each of those to do that. So we just need one barium and one oxygen, and that will get us. Again, the formula for the compound has no charge, but it is made up of two things that do have charges, a cation and an anion make it up. If I wanted to put together aluminum that has a +3 charge and sulfide that has a -2 charge, you want to think about here a common number between those two. So I have a 3 and a 2. If I multiply those together, that is 6, right? Is the common number between them. So to get my aluminum to 6, I need not one of them, but I actually need 2 of them, right? That will give me a +6. To get my sulfide to 6, I need not 1, not 2, but 3 of them will give me a -6 and a +6. At this point, I could write my formula. I have 1 and 2 aluminums, 2 to the right there. I have 1, 2, 3 sulfurs, and that will give me my proper formula here from aluminum sulfide, by the way, would be that name. This guy here would be barium oxide, ID. This guy would be aluminum sulfide, ID, right? Lastly here, if I look at my potassium, which is +1, and my phosphorus, which is -3, again, the common number between that is 3. So to get my potassium to 3, I need not 1, not 2, but 3 of them, and I just need one of those. So that's -3 balanced out by the +3, gives me to no charge overall. That's 1, 2, 3 potassiums, and that is 1 phosphorus. And that would give me my proper formula here, which would be potassium phosphide, IDE, from phosphorus. Drop the last part of phosphorus. Any questions on that? So whenever you put them together, you always want to make sure that the overall charge is 0. But you also want to remember that when you see any of these formulas, even though they do not have an overall charge, each of them is made up of things that do have charges, a cation that's positively charged and an anion that is negatively charged. By the way, sometimes people are taught to do this move. What were you using so far? And just go, all right, we'll go down, and that will tell you how much you need, Al2S3. And it does work about 92% of the time. It does not work 100% of the time. So if you're good with 92%, just blindly switch the charges down and up. Otherwise, you might want to think about getting it to 0 properly, because you will not get the right answer every time. Yeah. Any questions on that there? Okay. That wraps up chapter 4 here. Okay, so we're going to go again, jump ahead up to chapter 11. And in chapter 11, we're going to talk about modern atomic theory. We're going to talk about electrons ultimately in this chapter, electron configuration, some periodic trends, and what happens when electrons sort of transition from one energy level to the next. So as we talked about with Rutherford's atom, basically, we have that positive nucleus because of the protons. We have our electrons that are moving at a distance from the nucleus. Again, there is obviously an attraction between the negatively charged electrons and the positively charged nucleus overall because of the protons. The nucleus, again, is very small compared to the atoms. So the electrons make up a lot of the atom's space because they are flying around in that empty space of the atom. Now, some of the earliest ideas about how electrons sort of move about and what happens as electrons, for example, go to different energy levels. And one of the major sort of ideas that we're going to be talking about in this chapter is really this idea here. It's the idea that inside an atom, obviously, we have electrons. And electrons are on different energy levels. And there are different energy levels within an atom of where electrons could be at. And a couple of things can happen, for example, along the way to an atom. One thing that could happen is you could do something, or something can happen that's an endothermic process. We'll just draw my circle here as my atom. We can have an endothermic process where the atom is gaining energy, right? And it would be endothermic, right, for the atom. It will gain that energy. How could you do that? I don't know. You do like a flame test and stick it into fire, right? And it gets a bunch of energy. Maybe you run an electrical current, it gains some energy from electrical current. What happens in the case of the electrons within the atom is the electrons will gain that energy that's coming in, and they will get excited, and the electrons will move from a lower energy level to a higher energy level. So we'll get these electrons that will be basically increasing in energy level because the atom gained energy. So we'll pop them up here. So I'll get up here, maybe. Now, much like us and most things in chemistry, high states of energy is not really the best optimal sort of situation. Things like to be in a low state of energy. So what will typically happen, for example, is those electrons that got excited to higher energy levels will eventually work their way back down. And we'll say this electron maybe worked its way back down eventually to here. We'll just go down here to a lower state of energy. Now, the only way that the electrons, for example, can drop back down to a lower state of energy is the atom itself, in this case, as it's dropping those electrons down, will actually give off energy. And that obviously is an exothermic process, right, for the atom in this situation. There's a law of conservation of energy, which means energy cannot be created nor destroyed, which means as those electrons are dropping down, the atom will give off that energy in the form of a photon of light. And that photon of light is how that energy is going to be released from the atom. Now, for example, if that wave that comes off, that is that energy, has a specific wavelength in the visible part of the spectrum that we'll talk about. In the visible part of the spectrum is where we see color. So we'll see colors. This is kind of like what happens when you see fireworks, right? You launch fireworks, they explode the fireworks. Inside the fireworks, there's a bunch of elements. So as they explode, all those elements gain a lot of energy, and those electrons get excited. And as they come back down, we see pretty colors like yellow, blue, green, whatever it may be, and we're able to kind of see those colors. You probably also have done this maybe if you've ever like boiled water on your stove to make some pasta or something like that, and you have a flame for your stove there, as opposed to obviously electric, maybe not, but if you have a flame and maybe your water overboiled at some point and hit the flame, and you see the flame's color go from like a blue color to like a yellowish orangey type color, and that is actually like the salt that's in your water and the electrons in like the sodium being excited, and that's why it changes the flame color to that kind of yellowish orangey color for just a second. Then it kind of goes away and comes back to blue. So what we're talking about in this chapter really is partly through this idea of as electrons sort of gain energy, they will go from lower energy levels to higher. That is requires the atom to gain energy to do so. But as they come back down in energy to a lower state of energy, the atom's going to release that energy in the form of a photon. And again, that wave that comes off may be at a specific wavelength that corresponds to color that we see. It may correspond to heat or something else that comes off. So one of the earliest ideas was done by a guy named Planck, and he did a lot of work with radiation, and he heated solids at various temperatures. And he found that atoms and molecules only emit whole number multiples of sort of energy. And there's this idea that's known as this quanta of energy. And the idea of quanta of energy is that as these, for example, electrons transition from one energy level to the next, they will basically gain enough energy or lose enough energy to fully make that transition. And that's the idea of quantized energy, is they can fully make that transition. They will not stop halfway along the way. Sometimes it's referred to as like a staircase model, if you will. So if you're walking stairs, right, up or down, doesn't really matter, right? You typically have enough energy to make it to this step, right? To this step, to this step, or whichever step you are going up or down, right? You typically don't walk upstairs and go in between steps. I'm kind of tired. I'm just going to kind of rest in between the steps, right? Because you're going to fall. And that's sort of how electrons transition from energy levels. So, for example, when this guy gains energy, he will gain enough energy to fully make that transition all the way up to that energy level. He will not stop along the way. He will not vacation between energy levels or anything like that. He's going to get enough energy to always get up there. Same thing happens when he comes down in energy. When he loses energy, he will lose enough energy to completely get down to that energy level. Again, he will not find himself between different energy levels. And that's the idea of, again, a quantized energy or quanta of energy. Things will lose and gain enough energy to fully make a transition from one energy level to the next, especially electrons. Any questions on that there? And again, just like when somebody walks stairs, sometimes people have enough energy just to do one stair at a time, right? Some people maybe could do two steps at a time, right? And electrons are like that. Maybe you can gain enough energy to go 2 or 3 energy levels up or down, or maybe it can only will transition one energy level. So they can move multiple energy levels. But again, will definitely gain or lose enough energy to fully make those transitions wherever way they were going. Any questions on that there? So one of the earliest things was this idea of a quanta of energy, and Planck's constant, or Planck's idea that basically energy moves through space in the form of waves. So when we talk about energy moving, we talk about it moving in the form of waves. And that brings us to waves and some property, right? So we have a wave here, right, moving. And it's really the wave moving, right? And our bird here is just kind of going up and down. And if you've been in the ocean, maybe you have, obviously. If you hit by a wave, right? Certain waves have a little bit more punch than others, right? Some you could just kind of bounce through, and some, are a little bit stronger than others. And that's also true with energy. There is a relationship, as we'll talk about, between the energy of a wave, for example, and its wavelength, how long the wavelength is or how short the wavelength is. So let's talk about some of the properties of waves. First thing, property of a wave is lambda, or its wavelength. So when we talk about the wavelength, it is the distance between two peaks on a wave. And again, that is what sometimes abbreviated as a lambda. It could also be two like valleys as well, if you want. The frequency, which is nu, and it's not really a V, it's kind of like a V like that. Typically, though, with wavelength, we do see meters, centimeters, and nanometers. So remember, centi is 10 to the minus 2. Nano is a very common one, is 10 to the minus 9. So those are very common wavelengths. Frequency, which is a nu, is basically the amount of times a wave passes a point in a given second. It has units of reciprocal seconds, or a hertz, and they are related to each other. So one reciprocal second is a hertz, and a reciprocal second is also 1/seconds. It's sometimes written. So they're all basically a one-to-one relationship. And again, sometimes frequency is given in reciprocal seconds, sometimes it's given in hertz. So again, those are two common units of frequency. Amplitude is how tall the wave is from its midpoint there to the bottom, is the amplitude. And the speed of the wave can be found of a wave can be found by taking lambda, which is typically in meters, times the frequency, which is typically in reciprocal seconds. So typically when we talk about the speed of a wave, we're usually using units of meters per second. So meters per second is a common sort of unit that we use for the speed of a wave. That means, typically speaking, as we'll talk about shortly, a lot of times if you're doing some type of calculation that involves the wavelength, typically meters is usually the one you want to make sure it's in before you go into any formulas. So meters is sort of the proper unit to use, definitely in formulas for wavelengths, so everything cancels out correctly. So light behaves like electromagnetic radiation, which again is the emission of energy in the form of these electromagnetic waves. Now, there's also this idea that was thought about during this time of the kind of dual nature of light, and the idea that particles, for example, like electrons, can have wave-like functions, and waves can kind of behave like a stream of particles. So kind of the dual nature of light, that it could have some properties that are more like particles, and it could also behave as light wave-like functions as well. So we oftentimes will sort of see that characteristic play out later on in this chapter, where we talk about how electrons sort of move. As we'll talk about, they're sort of thought of as having a lot of wave-like characteristics of how they move about the atom. Now, you could think of a beam of light as traveling through space as these tiny packets of energy, which are known as photons. And as I mentioned before, there is a relationship between the wavelength, energy, and frequency. If you have a wave that has a pretty long wavelength, you have a long wavelength, you typically will have a lower frequency, and that usually will mean a lower energy. And that is opposite if you have a smaller wavelength or a shorter wavelength. A shorter wavelength usually means a higher frequency, and that usually results in higher energy. So the wavelength definitely has a determining factor on the energy. So things with very small wavelength pass through the points a lot of times per second, carrying a bigger punch, if you will, in terms of energy than things with a longer wavelength does. Any questions on that there? And again, here we can think of something like this as having wave-like function, and also we could also think of it as a stream of particles and packing a certain amount of energy associated with it. Even within color, we see the difference in terms of energy. Red here, which is what we see up here, has a longer wavelength. It's actually low